So it's time to finally meet the backprop algorithm, backpropagation of error, to give it its full name. What the name means is that we observe an error at the output units. That is, the network computed something but it got it wrong slightly. We have a good idea of what we wanted. And so we're going to take that error and propagate it backwards. That is, go back, work backwards from the output layer, from the error, until each individual weight, and then try to figure out how to change that weight to improve things. And as before, we'll do this once per pattern without making any changes until we've been through the entire data set, and then we'll do some weight changes. So, for revision, a trained network, when it's well trained, will have learnt a mapping such that the desired output patterns, seen on the right, appear at the output units when the input patterns, seen at the left, are presented. Now, the mapping that it's learnt is, strictly speaking, a mathematical function. It's just learning to do sums. And the parameters of this function are the weights. The variables in this function are the x values, that is, the inputs. So for the little network there, where I'm assuming sigmoidal activation functions at the hidden layer, I'm going to use tan h because it makes for cleaner equations when writing. It could be the logistic function, it doesn't make any difference. We know how this network works. We know that the output produced at unit 5 here is the sum of the tan h function computed at units 3 and 4 respectively, plus a bias. So in this particular network we have 1, 2, 3, 4, 5, 6 weights and 3 bias weights, so that's 9 parameters that would have to be learned. Those are all the W figures that appear in the equation. So the question posed is, how do we find those weights? And here's the possible solution. Guess them. It's not as daft as you might think. Computers are very, very fast. Random number generation is a well-solved problem. We could just guess the weights, and if we find it's not a good guess, we could guess again. This would take forever if you're doing it by hand. But it's a reasonable approach for fast machines and small problems. It's an interesting historical fact in neural network research that the literature is paved with people taking specific benchmark problems. We've met the exclusive OR problem, for example. It's a good benchmark problem. And showing that their new fancy algorithm outperforms all others and learns it more accurately or quicker or something. Because these benchmark problems are chosen to make clear certain formal features of the problem, like the nonlinear separability of the input patterns, they work well for illustrative purposes, but they make them very vulnerable to this particular approach. And Jürgen Schmidhuber and Sepp Hochreiter produced these two papers in 1996 and 2001, showing that the benchmark problems can all be improved upon. The state of the art could be vastly improved upon by the dumb strategy of guessing. But of course, those problems which have the formal characteristics that are interesting to theoreticians only stand for the much larger problem set of real messy problems with real world data, where the number of parameters may be several orders of magnitude larger. So this approach, while it's interesting and a good reminder that we are playing to some extent an abstract game of formal distinctions, it's not a contender for serious problems. For serious problems we need something like the backpropagation algorithm. We've already met the principle of gradient descent. That is essentially what we're doing here. We introduced it using that simple function like a hanging mesh there with a single minimum well defined, such that no matter where you started, if you went downhill on that surface, you would reach the minimum. That will in general not be true. The complex error surfaces shown on the right there, just as an example, is far more typical and we typically don't have an explicit representation of the error surface, so matters tend to be a bit more complex. Now I'm going to give just an informal account of backpropagation that is continuous with everything we've just seen. So there's only a very, very small addition to what we've already learned to make this algorithm work. Specifically, the core of this algorithm is a procedure for changing weights, and the generalized equation for weight change is given down there. The weight change to unit I from unit J will be, there's a minus sign because we're going downhill. The remainder terms will identify the gradient, and we want a negative gradient. Then we have the learning rate. I see I use eta and mu. I'm not very good at Greek, so I tend to use random Greek letters. That's the learning rate is the next term here. We've got some term delta there, which we'll come back to, and that's going to be differently instantiated depending on whether unit I is an output unit, for which we have a direct registration of error, or a hidden unit. They're the ones that cause the problems. And the last term in here is the activation of the feeding unit, unit J, because a weight originates in a feeding unit. That could be an input unit if it's feeding to the hidden layer, or an output unit if it's, the feeding unit could be in the hidden layer if it's feeding into the output layer. And we need to take the activation of the feeding unit into account, because if its activation was 0, it didn't contribute to the error. So, as before, for each pattern in the training set, we're going to compute errors. We're going to read them off at the output nodes, and in a manner just like what we already did, we're going to compute a suggested weight change for each weight in the layer of weights that is between the hidden layer and the output layer. Then we're going to go and iterate over the units in the hidden layer and compute that term delta for them. This is playing the role of error, but because these are hidden units, we don't have specific targets for them. So what we'll do is, for each hidden unit, we will compute what we call a generalized error expression, which will take into account its contribution to all the clear and distinct errors that we observed at the output layer. On the basis of that, we will compute a suggested weight change for each of the weights between the input layer and the hidden layer. And then after amassing all these suggested weight changes for all the weights and all the patterns, then we'll change them each a little bit as determined by the learning rate. So let's begin. Suppose we've presented a pattern P to the network and it produced some output, and we wanted it to produce -1, 0, 1, 1. But the output we actually got was 0.3, 0.2, -0.4, and 0.2. Lousy. So there's a lot of error here. We can enumerate the error for each of the output units separately. The error is always simply the difference between what we wanted, the target, and what we got, the output. So that's a simple subtraction. Our task here is to consider each weight in turn and to alter it in proportion to its contribution to the overall error. When the receiving node, node I, is an output node, we have this explicit computation that gives us the error at that node. It's very, very straightforward. When node I is a hidden unit, we'll have something else to do. So here's the only little bit of math you're going to be faced with. We're going to let E be the sum of the error at the output units. So we just add up all the errors at the output units. That's E. It's an overall measure of how stinky our network is, how well it's doing. Then the term on the right there with the fancy curly D's is probably unfamiliar to you. It's the partial derivative of the error with respect to the weight Wij. This is a formal mathematical quantity which can be unpacked using basic high school calculus. And what it means is it's a measure of how much the overall error, E, will change when we make a small change to Wij, assuming that everything else is held constant. So that term is going to be at the heart of our suggested weight change, which is simply going to be the negative of this, because this is actually a slope or a gradient. The negative of this multiplied by the learning rate. Now, the delta term in the delta rule will look different depending on whether node I is an output node or a hidden unit. For the output nodes, this is fairly straightforward. If our output node is a linear output node, that is, if its activation function is the same as its net input, then that delta term will be nothing but the error. It's just the error. More generally, however, our output units will typically be nonlinear units with sigmoidal activation functions. And in that case, we need to go back, as it were. Here's the backpropagation, one step in the backpropagation, when we need to go back from the error through sort of undoing the activation function to find out how much the net input should vary. The way to do that formally, and you'll have to take this on trust unless your calculus is up to speed, is that we multiply this error by the derivative of the activation function. Those of you who are panicking, don't worry. This is not going to get much more difficult, and it's a very simple idea. If our activation function is like this logistic function up there, its derivative is shown at the bottom right. It's a very simple function as well. It shows the rate of change of this function, which is maximum around 0, and towards the two tails of the function, for the extreme negative values and the extreme positive values, the derivative is vanishes. As it happens, the logistic function, which is a bit messy to write on paper, y equals 1 over 1 plus e to the minus x, happens to have a very, very simple derivative, which will allow us to compute this additional step very, very simply. So far, we know now how to develop a suggestion for a weight change if the weight lies between the hidden units and the output units. When the receiving unit is not an output node, but is itself a hidden unit, then the error term here is based on the error as seen across all the output units to which this hidden unit contributes. So the delta here is a bit more complicated, but if you look at the bit I've circled in red there, that sums over all the output units. K indexes those output units. Each of those had an error term, which was the actual error multiplied by the derivative. So we take the delta for each of the output units, multiply it by the weight that connects back to the hidden unit in question, and sum all those up. And this gives us something which is equivalent for the hidden unit to the direct error observed at an output unit. It is a distributed quantity because the hidden unit feeds multiple output units. But in this way, we can capture the importance of this hidden unit in the overall pattern of error that we see. Once more, because our hidden units are have nonlinear activation functions, we will multiply by the derivative of this in forming our delta term. So here's the steps of backpropagation. For each pattern in the training set, compute the error at the output nodes, compute a suggested weight change for each weight in that layer between the hidden units and the output units, compute that generalized error expression for the hidden units, figure out the delta W for each weight between the input and the hidden units, and then after amassing all the weights, all the suggested weight changes, and going through all the patterns, then we apply the delta rule and actually change each weight just a little bit. So it's only a very small extension of what we've seen already, the problem arose in figuring out this generalized error term. The solution to that problem that lies in the partial derivative that we saw. We don't have to worry too much about the details of it, but it's interesting to note that the simple application of high school calculus is sufficient to provide that term. And the death knell that was administered by the book Perceptrons was based on the unthinking assumption that activation functions might be discontinuous. So the perceptron had this stepwise linear function which is discontinuous, and therefore it doesn't have a well-defined derivative. Moving from a stepwise function to a smooth S-shaped function allows the tools of calculus, simple calculus tools, to be applied, and allowed for the backpropagation algorithm to be developed, which was released then with the parallel distributed processing books in 1986. You got through it. That's the most math we're going to do in this course. You survived. It's important that you note that nothing magic went on. Our very simple approach of doing very simple sums has been continued, and now we're in a position to develop networks that can learn desired input-output mappings from data sets.